Good. So I said that a large body of methods, literature, ideas can be understood in terms of the direct path problem, or more generally speaking, in terms of the semi-rings. And I think one nice example is the so-called Infimal Convolution, which opens a door to a plethora of practically used techniques that are usually summarized or that are part of what is called mathematical morphology. So here is how we wrote a generalized matrix product, or we could similarly write a generalized inner product. And you remember that convolution was or could also be expressed as matrix multiplication by multiplication with a triplets matrix. Or I can do it like this. I can write the standard convolution, a sum product convolution. And you see I have a sum here and a product. And now I replace by the operator from another single ring. So I replace sum by min, or here inf, the infimum, and I replace the product by the sum. Infimum is used here just because we're dealing with pluses and minus infinities, and this is gives you a bit of a cleaner treatment, or rather the minimum doesn't exist if we have minus infinity, and at least in this field where convolutions are used, people prefer writing then the inf rather than the min. Okay, so we have, or I can define a min sum or a tropical or an infimal convolution like so. Now, what does this mean? Let's do a picture. I am considering, here I've taken a row from some fantasy image, a single row, so I have gray value as a function of space. And so in the above formula, this thing here would be f, and then I have in addition this function g, which in this field is also called a structuring element, or I've abbreviated this as SE below. And well, what does it mean? My structuring element around the origin, it's 0. Then I can choose whatever I want as a structuring element, but this particular one, it's 0, and then it goes to infinity, and then to the right and left. So in all of this area, I cannot draw this very well, but let's say beyond a distance of tau and minus tau, this function g would be plus infinity. And now I will use this, I should have done a different symbol here. Now I will use this generalized convolution. Now if we look at this formula, what it does is that at each location y, let's say at this location y, it puts a copy of this structuring element, which goes to infinity, it's infinity everywhere, to the right and left, and we put such a structuring element at each and every location y. And then we take different color and then we take the infimum of these. Yeah, so the infimum over all y's means at a given, let's say at this location here, for example, I have a choice between this one and that one and that one. And I'm taking the infimum, so the lowest one. Yeah, so in other words, I'm here finding the lower envelope. And well, what will this function look like? It will essentially broaden, I mean, where the function is flat, this lower envelope becomes identical to the function. But outside, it will broaden my function a little bit. So I hope this is more or less right. So how did I find this? I said that here was still this function. Then at these locations here, it does not contribute to the lower envelope because it's shadowed or it's masked by this outlier that we had towards the bottom. And then here the function is pretty flat. Here my function has essentially been broadened. Peaks to the top we don't see at all. They get shadowed by what is by the neighbors on the left and right hand side. Yeah, so I think this looks reasonable. So I put my structuring function at all locations, and that means I have many responses at every location, and at a given location I take the infimum of all these responses, and that is this turquoise line that you have just seen. And yeah, here I practiced, and I think I get the same result. And when you apply this to images, you can get really intriguing results, where intriguing means actually helpful for certain problems. So as you see, outliers to the top disappear completely. And so if you have, let's say, an image with a few bright speckles, this would be a way of, for sure, getting rid of bright speckles. Now you have a great freedom in what structuring element you want to choose. For example, I can choose to use this parabola, and here I've used this very same test function f, the black one. But now you can, in your mind, put a parabola at each and every location. I want to draw the proper symbol here again. You can use a parabola at each and every location, and then use the infimum of all of those, and that gives you a turquoise line, which in this case will look different from the one above. And this infimal convolution in the language of mathematical morphology is called an erosion. So that would be the min-sum convolution. You can similarly define a dilation in terms of a max-sum convolution. So the structuring element for a max-sum convolution, for this to make sense, this should be upper bounded by some constant. Because if I did use the same structuring element, well, I would get infinity everywhere. That would not be very interesting. So you want to use, in the erosion, you want to use structuring elements which are bounded from below, and for the dilation, you want to use structuring elements which are bounded from above. Here are beautiful pictures from Benjamin Perret. He now applies this to a binary set where 1, in this case, where the black pixels have a value of 1 and the white pixels have a value of 0. And then you can erode this using, for example, this structuring element. And the result is that only the black pixels survive. So the black pixels are the result, and the gray pixels here, they're only meant to emphasize or to show the relation to what was the original picture. And now you see where the name erosion comes from. when you apply this to a binary image, then, well, it shrinks all of the things in the image a little bit. And if you have something which was thick, it shrinks, but it survives. But if you have something which was thin, then this is completely eliminated. And well, if you had here, you see this thin bridge. This bridge was also deleted. So previously we had one island with an isthmus in the middle, and now we have two smaller islands. Instead, dilation, makes everything a bit bigger, and now you can combine these operators in creative ways. And just to emphasize, what's the relation of these images to the images that I've shown above? Well, in the images above, I said that this was a gray value, and this was location. And now in these particular images shown here, well, the gray value is either always 1 or 0. Yeah, so this is also called binary morphology, and the other one is called gray value morphology. But the concept is the same. Yeah? So the binary morphology is a special case of the gray value morphology. All right, so we have operators like erosion and dilation. Here is a slide from Jean Serrin, who is one of the people who have been important in the development of mathematical morphology. And he gives an example of a noisy curve here, and it indicates the shape of the structuring element. So the structuring element here for the erosion is 0 here, and then becomes infinity to the right and left. The structuring element for the dilation, in contrast, is 0 in the middle, and then goes to minus infinity on the right and left hand side. And you see that this finds something like, in some sense, the upper and the lower envelope of this figure. All right, and I said that you can combine these operators in creative ways. So for example, you can say, okay, let's first erode. So in the binary case, you're going to make all foreground objects a little bit smaller, and the objects that were too small, well, they will disappear. And then you delete again. So the objects that you previously made smaller, you now make them bigger again. But the objects which disappeared, well, they remain disappeared. Yeah? So this is a way, for example, this opening of removing small objects. Vice versa, closing, what inverses the sequence of operations, is a means of getting rid of small holes in objects. And hence, this is also where the name of where mathematical morphology comes from, because it somehow deals with the shapes of things, with holes and islands and such things. So this is a concatenation. Here we have, you can also dilate an image and erode an image and take the difference between the two. That gives you the outline of objects, or there's something called a white or a black top hat filter, where you can take the original image and subtract it from it an opened image. This is what you see here on the right hand side. So we have some original image. We want to get rid of these big white blobs, and the top hat filter, well, if we, let's look again at the so what does it do? The opening here gets rid of all the small objects, and but it keeps the big ones. And then if we do original minus opening, well, the big objects disappear and the small ones come out. And in this particular case, the big ones were assumed to be dirt or something, and the small ones were supposed to be the objects of interest. This is an example here from Wikipedia. And I have another picture somewhere. So that would be the original, and then we have an eroded and a dilated version of it. And this is now more for illustration, but that kind of use case that you see on the bottom, you know, that's really something that you come across and that you want to use in real-world image analysis. And I've mentioned this COVID data analysis, which we had to do recently, and I mentioned that it needed to happen fast, and there was, you know, not enough training data and not enough time to train deep neural networks and such. So in such cases where you have no training data, not the time or the resources or anything to deal with a neural network, then you can use these handcrafted operators to great effect to get rid of certain kind of artifacts in your image. Yeah, so still, I think something very meaningful today in situations where you don't have a lot of training data. Okay, a special case of this. So I started by, you know, saying the algebraic path problem is so general, and then I mentioned the infimal convolution as a special case of this algebraic path problem, and now I'm coming to the distance transform as a special case of the infimal convolution. Okay, so we have this nesting of layers of abstraction to look at different problems here. And what is the Euclidean distance transform? So we have a couple of points shown here in black, and then we're interested in, well, finding the distance to the closest black point. That can be meaningful. Let's say, for example, let's say these are mobile phone antennas with the isotropic radius, and you want to find the spot which has the worst coverage or so. So you would want to know what is the point that's furthest away from any of the antennas or something like that. So on the left you see the distance as it increases from each particular node or element of the set. And if I now just want to know what is the distance from any point in the plane to the closest black point, but I don't care which one, well, then I take the infimum of all of these. So you see it's again some kind of lower envelope computation that we need. And in particular, now we could say we're interested in the Euclidean distance, or we could say we're interested in the squared Euclidean distance. And the squared Euclidean distance has the advantage of being separable in the sense of an infimal convolution, and moreover, in one dimension, this envelope can be found in linear time, which is amazing. Actually, this linear time complexity algorithm, that will work also for normal Euclidean distance, not the squared one, but the separability only holds for squared Euclidean distance. Why is it possible to do that in a linear time with a dynamic programming style algorithm? I think the answer is to do with Davenport-Chinsel sequences, which describe the number of alternating symbols that you observe and the computational complexity of solving associated problems. As far as I know, this distance transform in computer vision has not been discussed in terms of Davenport-Chinsel, but I think in an optimization sense, I think that is the underlying reason. Maybe when we have computer vision foundations and part 2 at some point in time, perhaps we'll talk about that more, or in some optimization lecture. All right, now where can you use distance transforms? For example, here in something called chamfer matching. So if we want to match the blue with the red, you see there's weak overlap, and if you do this on a pixel by pixel level, that will be difficult to see that it's essentially the same thing. But if you correlate instead the Euclidean distance transform of the blue and of the red pattern, then you will see that actually this is a good match. Or you can take the sparse pattern and overlay it on the distance transform of the other pattern, and that gives you much more robust matches. Or something where it's frequently used in bioimage analysis. So I mentioned last time that to detect nuclei, there is a very nice pre-trained neural network to do that, which is called StarDist. But if you don't want to use a GPU, or if you don't have a GPU or whatever, then this is a good way to partition convex objects which are overlapping. You first threshold, like so, then you compute the Euclidean distance transform, which looks like this, and then you run the watershed that we talked about last time, and you come up with the partitioning on the right-hand side. Yeah, so very versatile. So we've been talking about the Euclidean distance transform as a special case of informal convolution. And informal convolution was a generalization of the ordinary convolution that we know, a generalization in terms of another semi-ring, namely the min-sum semi-ring. Literature. If you want to read about this, the generic single source algorithm, then this is a nice paper. Very readable is this thin booklet here by Barash. If you are interested in learning more about the distance matrix product and in computing all pairs shortest path approximately, then I think the godfather of that research field is Uri Zwick, and he has a set of nice slides. And if you want to know more about a tropical algebra, then there is an online book here with a very readable chapter 7 introduction to this particular, also the algebra associated with a min-sum semi-ring. But as I said, there are all these other semi-rings, and really, the book is this one here. All right. I'm glad that I could tell you that I found an excuse to tell you about this body of theory, which summarizes much of what is actually being used in computer vision. Didn't have time today to talk about the efficient connected components, which would have been nice also. And next week we will look at min-cost flow as another very versatile primitive, which can, for example, be used to solve tracking problems in computer vision. And after that, I think I would like to talk about optimal transport, which is either that or optimal matchings, both of which are special cases of min-cost flow that are efficiently solvable and again have many applications in computer vision and beyond. And in the following week, I think I will do a Q&A for you.